this video, we're going to begin talking about the mean of raw data. When we're talking about the mean, most of us have grown up with the terminology average. We add them all up and divide by how many we have. Well, that is what mean does. The mean is computed by adding all the values of the variable in the raw data set and dividing by the number of observations. We have discussed the different types of data. We've discussed a population versus a sample. And from here on out, we're really going to need to pay attention. You've already heard me discuss the notation. I told you to get a notation page going with lowercase n being the sample size, capital N being the size of the population. Those are going to come back into play here. So when we want to calculate the population mean, that's just signifying that we're using all the individuals possible in the population. Examples of population mean would be taking the mean of exam scores for an entire class. If we're looking at the entire class, that is a population. Therefore, it is a population mean. Remember that population refers to parameters, when samples refer to statistics. And let me get this correct there. And it's denoted by a Greek symbol, mu. It's not an M or anything, it's a U with a long tail on the left side. We calculate this by taking each value in our data set and dividing it by the population size. So population mean, mu, is equal to adding all the values up. This right here is a capital sigma. We will use capital and lowercase Greek letters. The sigma just signifies summation. Means to add it all up. Okay? We're adding up all of the x values and we're dividing by the population size. The sample mean is calculated the exact same. We just have a little bit of different notation to it. It's still calculated adding all the data values up and dividing by how many you have in the sample. This is a statistic because it is from a sample. Remember that a parameter is from a population, a statistic is from a sample. The sample mean is denoted by an X with a bar across the top. That's called X bar. So X bar is the notation for a sample mean. You will notice that for populations, much of the time we will use Greek letters. For samples, we will use our normal alphanumeric letters with a little bit maybe of a different notation to it. Like here we have an X, but it's got a bar across the top. A lot of this is because the X represents just our data value. The X bar is going to represent the mean of that data value. Again, we still add up all of our data values and divide by n, our sample size. Again, this is a capital sigma and it just means to add everything up. So let's look at the following data represent the travel times in minutes to work for all 7 employees of a startup web development company. Notice it says all 7 employees. This is a startup company, therefore we are talking about a population. This data is a population. We want to compute the population mean of this data. So mu, which is this sigma symbol here, is equal to all the values added up, and I'm going to write them out for now. And we're going to divide by 7 because I've got 1, 2, 3, 4, 5, 6, 7 values. And of course it says all 7 employees. So I'm going to divide by 7. I'm going to write down an intermediate step, which is adding all these values up. If I add up 23, 36, and continuing, I get 174. I'm going to divide that by 7. So my mean is 24.9. And I'm just going to put the population mean travel time, because that's what we're talking about, is 24.9 minutes, because we are speaking in minutes. Let's look at part B of the same situation. Part B says take a simple random sample of n equal to 3 employees, meaning 3 employees from this sample above, and we want to find the mean of those 3 employees. I'm just going to start out by taking the first 3 employees that we were looking at, and they had travel times of 23, 36, and 23. This is going to be an X bar because it is a sample. And in this case, I'm only looking at 3 employees, so I'm going to do divide by 3. I'm going to add up the numerator, the top numbers, 23, 36, and 23. I get 82. Divide by 3. And I get 27.3. This is the mean for one sample. If I were to do this again, and notice that my answer in my calculator was actually this, and I just signified 27.3. I will discuss in just a moment why 27.3. Let's look at 3 other employees. I'm going to take the first employee, which was 23, the fourth employee, which was 18, and the last employee, which was 43. I'm going to add those up, and I'm going to divide by 3. So I do 23 plus 18 plus 43. I get 84, and I'm going to divide by 3, and I get 28. So sample means, notice, they're a little bit different, and it's based on your actual data values. If I had selected one of the data values with 5, so example, if I had selected 18, 5, and 26, I would have gotten 49 divided by 3. So my sample mean would have been 16.3 minutes. Notice I have a wide variety of sample means. The thing about sample means is it is only the fact that we took it from a sample of the population. Notice they are not our population mean. They're somewhere around there, but they're not going to be. Sample means differ from sample to sample. Exactly what I showed here. They generally do not equal the population mean because the population mean took into account all values. The samples just took into account some. Recall whenever I said in our calculators we got 27.33333, but I simplified it to 27.3. We want to always round the mean to 1 decimal place. Hold on a moment because I'm not finished. 1 decimal place more than the raw data. If we look back at our data, these values right here are what we consider raw data. Those are just the values that we collected. When we calculate mean and other aspects of this data, we want to look at, okay, notice all of our data here is whole numbers. I want one place more than that. So I want 1 decimal place. I want 1 decimal place. The reason why I keep 1 place more than the raw data is because I have done some calculations. I've chopped off some numbers at the back end. It's not a precise number. If I just rounded this to 27, 28, 16, it would not signify that I have done any rounding. Anytime that we round, we want to leave that additional place value to indicate that it has been rounded. Okay? So just be a little bit careful of that. The mean is not usually a typical value of the data. It may be a value that could not possibly appear in the data set, such as 17.3. For minute commutes, we were looking at discrete numbers. Well, 17.3 is not necessarily discrete. 16.3 is not necessarily discrete. Our mean, because it is being calculated, is not typically one of our data values itself. And it may be somewhere in between, which is fine because we have taken numbers and divided by something. The next item that we're going to measure regarding our data is what we call the median. The median of a variable is the value that lies in the middle of the data when it is arranged in what we call ascending order. Ascending order just means from smallest to the largest values. That's what ascending means. We are increasing, ascending up a side of a mountain. We use just a capital M to represent median, and this capital N doesn't matter whether it is population or sample. We use a capital M for it. There are going to be a couple of different ways for us to calculate the median of data. I'm going to show you both ways. So step 1 is going to be the exact same. Arrange the data in ascending order, from smallest to largest. Step 2 is to determine the number of observations, our N. Step 3 is to determine the observation in the middle of the data set. So the middle of the data set, median, it splits it into 50%. 50% less than, 50% greater than. When we have smaller data sets, what we tend to do is just mark off the largest, mark off the smallest, and keep going until we find that middle number, which works out great. We have to look at the fact that if the number of observations is odd, the median of the data set is exactly in the middle of the data set. So you can find this by taking N plus 1 and dividing by 2. We're going to take N plus 1 and divide by 2. If the number of observations is even, the median is in the middle of the observation set. It has 2 values actually, whenever we have even data sets. What we're going to do is we're going to take the mean of the observations that lie at position N divided by 2 and position N divided by 2 plus 1. So I know that that doesn't make a lot of sense to you right now. So let's look at our data set for our 7 workers. We have the travel times that they commute to work. First thing I'm going to do is I'm going to put it in order. 5, 18, 23, 23, 36, or I'm sorry, 26. Wanted to skip a number there. 26, 36, and 43. what I want to do is I want to determine n. n in this case is 7. 1, 2, 3, 4, 5, 6, 7. I have 7 numbers. When I look for the position, since this is odd, I'm going to look for position n plus 1 and divide it by 2. So I'm going to take 7 plus 1, divide by 2. So I get 8 divided by 2, which is 4. The fourth position. 1, 2, 3, 4. That is my median. The other way that I discussed was if I just start marking off one for one. One small, one large. One small, one large. One small, one large. Notice it's the exact same number. My median is 23. Be careful a little bit here. It doesn't really matter which way you do this. Just make sure that you put things in order from least to greatest first, and then you can proceed from there. Example 3 says that suppose the startup company hires a new employee. The travel time of the new employee is 70 minutes. So this person is traveling much further than the others. Determine the median of this new data set. Again, my very first step is I'm going to arrange the data in order from least to greatest. So I have 15, 18, 23, 23, 26, 36, 43, and 70. When I look for the position, my n is equal to 8 now. So my position, if I look at it the same way that I started to the other one, n plus 1 divided by 2, that's going to be 8 plus 1 divided by 2, so that's 9 divided by 2, which is 4.5. Notice it's not a whole number. In this case, whenever I get a position that's not a whole number, I'm going to take the mean of positions 4 and 5. So I'm going to take the mean of that number and the next one. 1, 2, 3, 4, and 5. So my median is going to be 23 plus 26 divided by 2. My median is 24.5. Another way to look at this is if I look at, remember in the previous one I marked off one for one. One small, one large, one small, one large. If I mark off a small and a large, I mark out everything. I take the mean of the two middle ones, which still gives me a median of 24.5. Let's look at the mean versus the median of some data. We still have the same original 7 employees. But this time, a new employee was hired that has a commute of 130 minutes. That's much longer than our 70-minute commute. And we want to know, how does this number impact the value of our mean and our median? So originally, when we were looking at it, our mean was 24.9 and our median was 23. This is of our original data set. So these 7 employees. Let's take a look at what happens whenever we find the mean with the new employee. The mean with the new employee would be to take 23, 36, 23, 18, 5, 26, 43, plus 130. I'm going to divide by 8. I get 304 divided by 8, so my new mean is 38 minutes. there's quite a bit of difference between the original mean and this mean. Let's look at the median. Let's look at what happens to the median. Again, I must arrange them in order. And so I have 5, 18, 23, 23, 26, 36, 43, 130. Let me get that 130. For small data sets, to me, it is much easier to just mark off one small for one large, one small for one large, one small for one large. I have two values. My median is 23 plus 26 divided by 2. My median is 24.5. Notice that a person with a 130-minute commute versus when we added a person with a 70-minute commute, the median didn't change any. Also notice that the median from the original to the new didn't change a whole lot, but the mean sure did. Notice that there's a larger change in the mean than in the median. The reason this is because we call the median is not affected significantly. There's very little change. So a numerical value of data is said to be resistant if extreme values, very large or very small, relative to the data do not affect it substantially. Mean takes into account all of our data values. Because it takes into account all of our data values, including the extreme numbers, it changes significantly. Mean is not resistant. Median, on the other hand, is resistant. It only takes into account the middle two numbers. I could add a number down here and a number up here, a number down here and a number up here. It wouldn't matter. My median would still be the same because it's only looking at those two middle numbers. We can look at the relationship between mean, median, and the distribution shape as well. In a symmetric one, this middle one here, the mean and median are approximately the same because we have some small, we have some large, but most of our data is in the middle. When we look at the left skewed data, here I have a value or two that's extremely low compared to the rest of my data. Think about exam scores. You're going along, you're doing okay, you miss a test, you get a 0. What does that do to your class average? It brings it down drastically. It brings it down drastically. Your median grade is still approximately the same, but your mean has dropped. Therefore, in a left skewed, my mean is less than my median. Here's a hint. If you put mean, you put median. You put mean on the left, you put median on the right, mean on the left, median on the right. Whichever side it's skewed to, that's the direction the arrow should point. Here it's not skewed, so they're going to be equal. Here it is right skewed. You've been making bad grades, bad grades, bad grades. Then you make 103. Well, that brings your mean way up. That brings your average way up. So mean is greater than your median in that case, whenever it is right skewed. Looking at mean and median, there are some advantages and disadvantages. The advantages to mean is it takes into account every data value. Those high grades are great for us. It pulls us on up. The low grades, it pulls us way down. That's kind of a disadvantage. Highly influenced by extreme values. It's not resistant. Think about a company. When you look at the income of all the employees in a company, the CEO, the CFO, they're going to make much more than the janitors who are still employed by that company. When you look at it, those extreme values, one way or another, is going to shift the average income of that company. The higher away from everybody else that the CEO makes, it's going to look really good for the company because, hey, our average salary for our employees is $75,000. Never mind, nobody actually makes $75,000 except the CEO. CEO makes $180,000. But because that one outlier, it pulls our mean up, pulls our average income up. Just like in the same case, if you look at your paychecks, your average paycheck could drastically go down if you're an hourly person. In other words, you get paid by the hour. Think about weeks throughout the year. You're working approximately the same. Then you get sick for a week or so. Or you take a vacation and don't get paid for that vacation. That zero paycheck still gets averaged in, and it brings your overall income average down. But the median, it's resistant. So it's not dependent on all of the data. It just looks at your middle values. The disadvantage is it looks at only one or two values. So the advantages and disadvantages of mean and median are kind of the same depending upon how you look at them. Are they a good or a bad thing? Practice getting your mean and your median, and let me know if you have any questions.